It is, isn't it?
Time we got.
It will take 55.
Where's the sheet?
Second.
In the spring. But not.
Oh, not the detail.
Oh, yeah, we have access to the, yeah. That,
Yeah, oh, I know, but. You know. The newspaper is just a bunch.
it's hard to search.
Because like. Constellation.
I'll have to leave around 9:45 because I'm helping a different student with their presentation.
So they're right next door.
Yeah.
Right.
Oh, okay.
She's my boss.
Oh,
So
there we
like-
go, we're going. What was your name again? Sorry, sorry.
I know. Nice to meet you.
Sorry, I didn't introduce him.
I should have done it.
What?
It's fine.
Hi.
Wow.
Hello.
Welcome to join us.
So I am coming up too,
Yeah.
so.
We'll stay far.
I'm
Yeah,
sorry.
right, yeah, be up there.
And you're,
Yeah, and you're.
We went through the UW program. Yeah, a lot of.
oh my God.
What?
Yeah, we're happy to be in the field. As you can tell,
Yeah.
you know where we'd rather be. Thank you. We're ready to go. Yeah, are you have it working online? We
Yeah,
have a couple minutes. I did see Anne, so I know she's coming up.
okay,
Yeah.
Okay.
Your parents online?
Yeah.
they are.
That's great. Oh, man. Your dad wants to be here.
Of course.
Yeah, of course, yes.
Oh, is your mom Laura? I just saw her. from-
Laura?
Hey, from Laura.
Oh, they can hear us.
Oh,
Yeah,
oh,
they can
sure.
hear
That's
us.
the heart.
Laura is my sister.
Oh, hi, sister.
And now
Yeah.
they can see us.
Dad.
Oh, we got
Yeah.
another one.
Matthew
and
is
she's
also
so
connect.
Love it.
Oh, I should. Is it okay?
Oh, no, she showed them already.
Oh, you did?
Yeah.
Okay.
But should I have, the Fish and Wildlife contact tell the inspector that they're working with us?
That should be perfect.
Well,
You're at like 7 degrees. It would help a lot.
okay.
Gosh.
Yeah. Now we can begin, I think, when you're ready.
Okay.
Yeah, actually, are you expecting anything else? Okay.
As far as he told me he was gonna. Get on.
Or-
Jorge.
Oh, no, okay, I think I'm ready now.
Can we see who's on?
Oh, on the Zoom? We have the Zoom here.
Okay.
Karen,
My two sisters.
Okay. Sounds good.
Okay. Okay.
Yeah.
Okay, everyone. Welcome to the project defense for Victoria Pena. She's It's been great to work with her. Are you trying to sell your heart there?
Yeah.
You know, everyone's all friends here, and it's gonna be a fun event. So
A celebration.
a celebration,
Your success.
yes, and of your hard work. You know, I don't think I've ever worked with a more hardworking student. Okay, just making sure I didn't work with you guys. So a hardworking student, and it's been a joy and a pleasure to work with you on the project Dynamic Coefficient of Friction Testing at 2 light rails
Train
train
station.
stations. So Victoria's going to present her work, and there'll be opportunity for the public to ask questions, as well as people online. If you want to ask questions, you can send them in the chat. And then we'll kick you guys out. We'll have an opportunity to ask questions, and then we'll bring her back in and discuss things with her. Take it away.
Good morning, everyone, and thank you all for being here. Today I'll be presenting my final project, Dynamic Coefficient of Friction Testing at 2 Sound Transit light rail stations. In this picture, you can see the 3 main characters of this story. Mari Cohen, Marisa Baker, and who's presenting today, Maria Victoria Pena. This presentation will follow the structure of the written report. I'll begin with the background on sleep biomechanics and previous research. Then I'll outline the methods used in the field testing. I'll present my descriptive results, the statistical findings, and some post hoc comparisons. Finally, I'll interpret these results from an industrial hygiene perspective, and I'll conclude with some recommendations for sound transit. So why do we care about sleep resistance? So sleeps generally occur when the foot is already in motion, which is why static friction is not a real representative of the sleep risk. Instead, the dynamic coefficient of friction allows us to quantify the kinetic interaction and evaluate how contaminants like water reduce the available friction in the surface. Ultimately, higher friction corresponds to lower probability of sleeping, making the dynamic coefficient of friction a more relevant metric for injury prevention. Some evidence from laboratory and field testing, some prior studies highlight that portable tribometers, slider harness, and protocol variation can all affect measurements in different ways, which is why calibration and standardization are essential. Some research also shows that ceramic tiles and smooth concrete lose friction rapidly when they are wet, whereas microtextured and porosity surfaces modify this behavior. Across these studies, moisture and very thin water films consistently emerge as dominant contributors to friction loss. These findings establish the rationale for testing under different moisture conditions, dry, damp, and wet. The British pendulum tester, which is the device we use, remains widely used because it is portable, it is reproducible, and biomechanically relevant. It simulates the heel strike and captures the dynamic friction to reflect real pedestrian movement. Its validity has been demonstrated in pavement engineering and in sleep biomechanics, where pendulum values correlate well with the sleep probability. This cross-disciplinary acceptance supports its use in transit environments, like the sound transit stations. Some interesting facts: the British pendulum tester was originally developed in the United Kingdom back in the 50s to evaluate skid resistance of the road surfaces. There is no single universal sleep resistant threshold. Instead, several standards provide frameworks for measurement and interpretation. The American Society for Testing in Materials, ASTM E30322, specifies the test procedure, but leaves the acceptable ppm values at the discretion of the user. The United Kingdom Sleep Resistance Group defines their score for high, moderate, and low risk potential using the same ppm values that are in the scale of the pendulum. The British and European standard, the BS-EN 16165, 2021, emphasizes the consistency and comparability of results across all different European standards. The US style standards that are American National Standard Institute, the A137.1 and A326.3, recommend minimum wet dynamic coefficient of friction values, while the National Floor Safety Institute provides performance categories for walkways. Together, all these standards guide how the data should be gathered and evaluated. The central question guiding this project was first, how sleep resistance varies across moisture conditions, dry, damp, and wet, on tile and polished concrete surfaces at Seattle Airport Station and the University of Washington Stadium Station. A secondary question was whether commercially available surface treatments like a stone grip from Sleep Doctors and sparkles of coating provide a meaningful improvement over the untreated surfaces. So we might think from the observations to untreated surfaces when they are wet, we can see an increase on the incidence from slips and falls. So we might think that by adding this coating, we will reduce the risk. That's our rationale. That's what we think. So we wanted to find statistical data to see if that improvement was significant. Some background on the slips and fall incident from 2013 to 2025. Sun Transit recorded over 920 slips and falls self-reported incidents. 3 stations, including the Seattle Airport, account for nearly half of these incidents reported. At Seattle Airport, most incidents occurred in the escalators, but the mezzanine and platform also record a relevant rate. This data reinforced that wet conditions and certain flooring materials contribute to higher incident frequency, supporting the decision to evaluate these specific stations. Here's the device we used. The British pendulum tester measures the energy lost when a rubber slider contacts the test surface, reported as a British pendulum number. So we can tell that when a surface is more resistant, the slider can swing further. I think I have a slider. This is my slider to simulate the slider from the pendulum. So you can imagine that when the surface has a higher friction, my slider can't swing any further. When I have my surface wet, or when the surface is very slippery, like polished concrete, my swing will travel further. Then I will get lower values. Higher friction, lower friction. This device directly simulates heel strike dynamics, making it appropriate for pedestrian sleep risk assessment. Its sensitivity to moisture and contaminants is aligned with the goals of this project. We conducted a response verification to ensure quality and accuracy of our data. So the device level, zero position, and sensitivity were verified per ASTM E303 procedures. We did 3 free swings to ensure that the pendulum returned to zero. And then we calibrated on that 3-micron lapel film paper, which is the pink paper you can see in the video. We know the resistance value of the paper, which is 65 plus minus 3, to confirm that the device was responding correctly to those readings. These checks were repeated before and after every field session to ensure that the variation that we were observing on the pendulum actually corresponds to a variation of the surface without any instrument drift. For the sampling, we did in Seattle Airport and the University of Washington Station. We selected this station due to its high ridership, the high moisture exposure, the diverse fluorine materials that we had. We had at the University of Washington Station, we had tiles treated and untreated. And the Seattle Airport, we had untreated tiles, polished concrete, concrete treated with sparkle tuff, and concrete treated as driveway. The conditions, and they also represented stations with high rates of slips and fall. So the conditions at these stations are realistic for evaluating public exposure context. These are the sampling locations from the University of Washington Station. We selected 2 locations in the platform and 2 locations in the mezzanine. Every spot corresponds to high and low traffic. High traffic are the yellow numbers and low traffic are the green numbers. And in the platform level, we had the tiles untreated, and in the mezzanine level, we had the tiles treated with a stone grip. At Seattle Airport Station, we did 8 different sampling locations. In the mezzanine level, we had the sparkle tuff and the polished concrete. In the platform level, we had the untreated tiles. This provides us an opportunity to evaluate real-world treatment performance in the case of the sparkle tuff. The testing followed ASTM E303 and BS EN 1665. So we started by cleaning the surfaces. Then, according to the condition that we were trying to assess, we apply water. For the dry condition, we didn't apply any water. For moist condition, we did 2 sprays of water, and for wet condition, we did 4 sprays. Then we took 8 readings at 0 degrees. Then we rotate the pendulum at 90 degrees and repeated the procedure as wet, damp, and dry. The remaining at each side, we recorded the eight readings in this form that you're watching. We then discarded the first 3 readings to allow a slider conditioning, and the remaining valid swings were averaged to produce a single BPM value. So you can see the last 5 readings from the wet condition at 0 degrees and the last 5 readings from the wet condition at 90 degrees were all averaged to produce 1 BPM value for this sampling location at wet condition. The same for damp and the same for dry. The BPM values were interpreted using the UK SRG slip potential framework. All the values below 25 indicate high slip risk. The values between 25 and 35.9 moderate risk, and below and above 36 low risk. This UK classification is widely used for pedestrian surfaces because it provides a practical interpretation of the BPM values in terms of injury risk, which is a term that safety professionals and industrial hygienists are fairly familiarized. Before jumping to the stats, I would like to recall something that Professor Julia used to do on her lectures. Professor Julia was a professor from toxicology, and she was very thorough. in her classes. And she often liked to add like extra content to her presentations, and that content wasn't included in the module. So before she started talking about this extra content, she also said, you don't have to worry about this in the final exam. This is just to give you a flavor. When we were actually doing the final exam, we were all like, but it was just to give us a flavor. So yeah, the statistical analysis, it is not the main component of my project. My project focuses on interpreting the ppm values from an industrial hygiene perspective. But the next 6 or 7 slides talking about the statistical model is just to give you a flavor. So to analyze statistically your data, I used the software RStudio to run an aligned rank transform ANOVA. This is a non-parametric test for factorial designs when data doesn't meet normality or equal variance assumptions. It works by aligning and ranking the data, so the main effect and interaction can be tested fairly across the groups, even when the groups have different sample sizes. In this model, we have different variables, but we just focused on the F value and the P value. So the F value represents the ratio of the variance between groups over the variance within groups. So as higher, it is a unitless variable. So as higher is this F value indicates a stronger evidence of a real effect. The P value tells us whether that F value is statistically significant or not. So P values under 0.05 means that effect is unlikely due to chance. So we can conclude there is a true difference among the groups. It is also important to distinguish, okay, why did we use the mean BPM and why we didn't compute our entire data, because each location is the actual sampling unit, while the repeated 5 readings are technical replicates, not independent observation. The only independent observation is the ppm average per condition per location. So using the raw readings will artificially inflate the sample size, a problem known as pseudo-replication. Averaging the valid readings per condition per location provides a statistically appropriate data set for the ANOVA testing. This table lists the mean BPM values for all 12 locations. So as expected, nearly all surfaces show substantial decreases when they move from dry to damp to wet. The untreated surfaces often drop sharply into moderate or high slip range when these are wet, whereas the sparkle top remain as with high BPMs even under wet conditions. We group our data according to the treatment. So we had 5 groups, 3 for the concrete coated with the sparkle top, concrete treated with a dry way, and the just polished concrete. We call it concrete untreated. And for the tiles, we had 2 groups, the tiles treated with the stone grip coating and the tiles untreated. This box plot illustrate the distribution of the BPM by treatment category and moisture level. Across all materials, BPM decreases as moisture increases. Here is a detail of the result of the test for normality and heterogeneity. In the Shapiro wheel, which is a test for normality, to evaluate normality of our data, we found that 11 groups from 15 had p-values under 0.05, meaning those 11 groups are not normally distributed because the majority of our data set is not normally distributed. We can't use a parametric test. In the Leibniz test, we had an F-value of 7.54 and a p-value showing it is significant. That means the variance across the groups are not the same. We finally run QQ plots that confirm skewness. We can see some outliers in the red circles. So these three tests, the Shapiro-Wilk, the Leibniz, and these QQ plots are essential to decide what is the appropriate test to answer our research question. They supported and validated the use of a factorial design, non-parametric ANOVA. These are the results we got from the model. The model showed significant main effect of treatment and condition, as well as a significant interaction between these two. This means that friction are different between treatment types. And the effect of moisture, it is also different across these treatments. In plain words, treatment perform differently depending on whether the surface is dry, damp, or wet. These interaction plots illustrate that lines are not parallels, confirming that there is a treatment condition interaction. The sparkle top shows consistently high BPNs regardless of moisture, while untreated surfaces drops sharply from dry to wet. This visualization reinforces the statistical finding that treatments do not perform equally across moisture levels. The post hoc showed that sparkle top significantly improved the friction surface compared to its untreated counterpart. On the other hand, dry weight coating and stone grip on tiles did not produce a statistically significant improvement. This indicates that only one of the tested treatments produced meaningfully altered the slip resistance. From the moisture contrast, all were significant. Dry is higher significant than damp, and damp is higher significantly than wet. This just confirmed the expected trend we had before the study that is gonna behave that way. This heat map summarizes the mean and standard deviation of the BPN values ranked by treatment and moisture. The red areas indicate high slips, the yellow moderate, and the green low slip potential. Again, the untreated tile and untreated concrete show the higher slip potential when wet, whereas sparkle top remain in the low risk category. The results strongly show that moisture is the primary driving factor slip risk across all tested surfaces. The treatment type can influence the outcome, but only sparkle top showed a significant improvement. Overall, untreated tile and untreated polished concrete transition from safe to hazardous when wet. These findings directly support the research question by quantifying how moisture impacts the traction. From an industrial hygiene perspective, slipperiness can be viewed as a physical hazard resulting from an inadequate friction. In the hierarchy of controls, we favor slip-resistant surfaces, such as textured concrete, because these eliminate the hazard in the source. The surface coatings function as engineering controls, but they may pose chemical exposure during the application, during the cleaning, during maintenance, and in future, it might require reapplying. So understanding both friction performance and worker exposures is critical to make informed material selection. Some practical recommendations for sound transit. They can benefit from adopting sleep testing protocols, setting minimum wet BPM threshold for their stations, and periodically reassessing the surfaces as the coatings age with time. Long-term strategies include texture surfaces, improving the drainage, and optimizing their cleaning protocols. These preventive measures are durable and reduce the dependency on coatings. To conclude, moisture causes substantial reductions in sleep resistance, with untreated surfaces becoming hazardous when wet. Sparkle Top was the only treatment that that provided significantly higher wet condition traction. These findings support performance-based material selection and emphasize the importance of an early involvement of the safety and IH professionals in the design stage of these public spaces. Ultimately, data-driven evaluation can improve pedestrian safety and reduce the burden of sleep-related incidents. Thank you.
Thank you. Excellent job. Now you can take a breath, okay?
You're getting a lot.
Yeah.
Laurita. I'm gonna drink some transit water.
Don't spill it on the station.
The carpet's gonna be wet. It's slippery too. Okay, are there any questions from the audience? If you have questions in the chat or on Zoom, just put them in the chat.
Two questions. One, when you turn the machine 90 degrees, you go wet and dry.
We started dry, then wet at 0. And because the surface was wet, we continues when we turn wet, then dry.
And how does the permanent go on the wet? Or did you let it dry all the way and pour through?
Between swings, we dry the surface with paper towels.
We had a damper here.
Oh yeah, and we had a humidity meter.
Okay, thanks. And then my second question is more about sound transit. Why don't they just cover everything with fresh? Are tiles prettier or cheaper? Or the cleaning issue?
I think they still figuring out that question. That's why they ask Marisa and Mari for technical guidance on what to do.
Got it.
Because yeah,
Actually, it was like design based on how nice it looked.
Yeah.
Now they're realizing-
Architects.
architects,
Architects.
the
One word,
decisions.
architects.
Got it.
But I also think that there was a mandate when it was passed that there has to be, there has to be an aesthetic element to the new stations. And some of that is when you go through the stations, you'll see art, local artists, but I think it's, yes, architects designing for aesthetics as things mandated.
Got it. I was surprised that the platform level had more of the not treated concrete. I don't know, for me, it was seen that.
Well, the treated concrete was only treated because they were doing tests. So it wasn't full blown. It was just tests, so we could test it.
It was just the corner. If I can show you the map, there were 3 dots in one corner of the mezzanine level. They just applied the coating in that corner for us to test. Yeah.
Oh, no kidding. Well, all of us who do
All of
this,
us,
well,
yeah.
We are constantly looking and evaluating the slipperiness.
And measuring with their foot. How is slippery? Yeah, I did that after the project.
You
Yeah.
become like a human.
Yeah, yeah.
Human slide.
Yeah, I can just measure with my foot.
Well, actually, right up there where the red bricks were red.
Oh,
brick.
lickety.
Yeah,
Yes,
this
that's
isn't good either down here.
Okay.
Yeah.
Yeah.
For servants for.
Yes.
Yeah.
Yes.
And the concourse
Yeah,
at
for the
Husky
blood.
Stadium.
Okay.
Okay, any other questions?
I thought you did a great job at the end summarizing, you know, why eliminating the physical hazard is important. And then you talked about some of the chemical exposure risks of the coatings. And I was just curious to know, like, where did you find, what kind of data did you find about that? Or, you know, have there been measurements when these things are being applied? Has anybody worked on that?
So I know that applying those coatings, the stone grip and the sparkle soft, the stone grip is an acid etching fluoride compound and might pose exposure to organic volatile compounds. It is also very corrosive to the skin, to the eyes, so the person has to be fully protected, fully geared. The exposure might depend on whether it is a closed space or it is an open space. That's a big driving factor, or whether before deciding what is the right respiratory protection. In the case of the sparkle tough, it is silicone epoxy hybrid. It is also corrosive to the skin. It might pose exposure to particulate material, so it is a different protection than stone grip, and it is the same story. We might need to evaluate the ventilation of the space if we are working on a closed station or an open station, you know, to protect the worker during the application.
Okay, great, thanks again. Okay, why don't the public leave? And I think Kevin, now you can cut the Zoom. Thank you all from in Colombia from joining in for this presentation. It's been wonderful working with your daughter and sister.
Bye.
You can go.
Oh, Matthew is also connected.
Yep, it was it.
Matthew, he had his dissertation last Monday.
Oh, okay.
Yeah. Okay. I should leave the Zoom.
Yeah.
Yes.
Okay.